Welcome to Mrs. Z's Chemistry. In this lesson, we will learn about reversible reactions. Most of the reactions that we've encountered so far are completion reactions. This means that all of the reactants turn into products. The reaction doesn't stop producing products until one or all of the reactants runs out. Most of the reactions we encounter are actually called reversible reactions, which means the products spontaneously turn back into reactants before all of the reactants run out. Not all of the reactants get to turn into products. An example of a biological reversible reaction is hemoglobin binding to oxygen in our lungs. This molecule here is hemoglobin, and I'm abbreviating it here as HB. In this chemical reaction, and you can see that it reacts with 4 oxygen molecules and turns into something called oxyhemoglobin, and it is the hemoglobin molecule with the 4 oxygens connected to it. This reaction's ability to reverse is crucial for oxygen transport in the blood, because later this oxyhemoglobin this whole reaction reverses and the oxyhemoglobin turns into hemoglobin that is separate from the 4 oxygens, and the 4 oxygen molecules are released into the cells. The hemoglobin molecule then travels back to the lungs to bind with 4 more oxygen molecules. Combustion reactions are completion reactions. Once a hydrocarbon, a molecule with carbon and hydrogen like this one in this example, or it could be fuel or candle wax. Once it burns in the presence of oxygen and turns into CO2 and H2O, this cannot be undone. The CO2 and H2O can't spontaneously turn back into an unburned candle. This is a one-way process, and we use a one-way arrow like this to represent it. Most reactions don't go to completion, and here is this example. We have the molecule N2O4, and it spontaneously turns into 2 molecules of NO2. This substance, the N2O4, is teal. So at time 0, if you had a closed test tube full of N2O4, it would look clear. Once the molecule starts decomposing into NO2, as you can see some of the NO2 molecules here, the test tube will start turning a light brown color. And at equilibrium, we have a lot of NO2 molecules, but we also still have some N2O4. Not all of the N2O4 gets to turn into the products. And this is because 2 of the N2O4 molecules will turn back into, 2 of the NO2 molecules will turn back into the N2O4 before all of the N2O4 get to turn into products. And this reaction keeps happening in both directions. And we use a two-way arrow to represent this. It could look like any of these to represent the two-way arrow. This reaction is taking place in a closed system. So initially, we only have the reactant, N2O4, and that's right here on this graph at time 0. And at time 0, we have 0 of the product. But as time proceeds, in the x-axis here, the amount or concentration of our reactant starts to decrease until it levels off. And the amount of the product begins to increase until it also levels off. The concentration of N2O4 starting out here decreases, and the NO2 starting here increases. And for every 1, because the coefficient is a 1 here, of N2O4 that disappears, we have 2 of the NO2 appears, which means the product is increasing twice as fast as the reactant decreases. The decreasing concentration or molarity of N2O4 slows the forward reaction, and the increasing concentration of NO2 speeds the reverse reaction. Eventually, each species maintains a specific concentration, that set amount right here and here, though not necessarily equal to each other. So nature pushes each chemical reaction to equilibrium. And each different chemical reaction, here's just one of the examples we've been looking at, has a different ratio of products to reactants that exist at equilibrium. Some reactions create more products, like this example here. We have a greater amount of NO2 than we do of N2O4 at equilibrium. But other chemical reactions will end up creating very few products before reaching equilibrium. Rarely are the products equal to the reactants at equilibrium. Equilibrium is achieved when the rate of the forward reaction reaches the rate of the reverse reaction. So on this graph, we have rate being calculated on the y-axis, and time is still on the x-axis. So you can see that the rate of the forward reaction starts out up here, and it slowly decreases as the N2O4 amount decreases. The rate of the reverse reaction is sitting here and starting out at 0, but then as N2O4 turns into NO2, the rate of the reverse can increase until both of the rates of the forward and the reverse are equal to each other. Remember, the concentrations are not equal to each other, but the rate of the forward and the reverse are equal to each other. Once equilibrium is established, we can observe a few things. One is that there are no concentration changes happening. So if you counted the concentration of the products versus the concentration of the reactants, they would stay the same amount from the beginning of equilibrium until as long as it stays at equilibrium, but they are very rarely equal to each other. Species in this context just means any atom, ion, molecule, or compound, or any particle in any of the different states of matter, gas, liquid, or aqueous. So the concentrations of all the species, all the particles, are going to remain constant, but they're rarely equal to each other. The ratio between the products and reactants will remain constant while at equilibrium. So nature not only pushes each chemical reaction to reach equilibrium, but it also wants to maintain equilibrium. And equilibrium is maintained in a closed system. As soon as you open the system or open the lid, some of the reactants and products could leave the container, assuming they were gas particles, and also other gas particles might enter the system or the container. And this would mess up the equilibrium system. The volume of the system must maintain in a constant volume, and the temperature also must not change. If the temperature changes, then the ratio between products and reactants will also change. Here are two different examples of equilibrium. This first one is a physical equilibrium. We call it physical because the substance CO2 is not changing, only the state of matter from gas to aqueous. In a sealed bottle of soda, we have CO2 particles dissolved in the soda, which are the aqueous CO2, and in between the space of the top of the liquid and the lid, we have gaseous CO2. For every gaseous CO2 molecule that dissolves into the liquid, another aqueous CO2 comes out of solution and turns back into a gas particle of CO2. In this chemical equilibrium example, we have NH3, ammonia, reacting with water. One hydrogen ion is transferred from water to the NH3, so this turns into NH4 plus and OH minus. Very few of these reactants, the NH3 and H2O, actually get to turn into products. Many of the products then turn back into reactants. This is an example of a weak base reacting with water, and we're going to learn more about weak acids and weak bases versus strong acids and strong bases in our chapter on acids and bases. So let's go over a summary of equilibrium. Equilibrium can only be obtained in a closed system. The rate of the forward reaction is equal to the rate of the reverse reaction. The concentrations are very rarely equal to each other. The catalysts do not shift the position of equilibrium, but they could increase the rate at which equilibrium is achieved. The concentration of the reactants and products remain constant. Their net change is zero, but they're not necessarily equal to each other. This TED-Ed video uniquely explains chemical equilibrium, and I think you should go watch this video, and I will link it in the description.